Okay, hello everyone and welcome back to your YouTube channel and welcome to this amazing video of today. I have an amazing video and today I will be talking about the electromechanical constants that we use for analyzing power system dynamics. But also I will use the swing equation for some basic calculations, okay? The basic calculation that we are doing today is basically calculating acceleration and changes on the rotor angle, okay, during a disturbance, okay? In this case, the disturbance is just basic change on the power balance, okay? But let's start to talk about this example. This is the example number 3, electromechanical constant and acceleration calculations, okay? And let's consider a gas turbine, and this is a gas turbine generator, of course, using a synchronous generator, and this is a 4-pole synchronous generator, and it has a rate apparent power of 50.34 MVA, okay? And the power factor, the rate power factor of this generator is 0.8. Nominal voltage, 10.5 kilovolts, and this is a 50 hertz generation unit. And finally, we have here the rotational inertia constant H, and you can see over there 6.96 blah 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 megawatts over MVA. And there are three interesting questions over here. Question number 1, you can see there is a question number 1, determine the stored kinetic energy in the rotor at synchronous speed. Then we have question number 2. When the generator is supplying a load, there is a load connected to this synchronous machine. The load is 10 megawatts. The mechanical input is increased by 10 megawatts. Now the critical question here is, what will be the rotor acceleration alpha in electrical degrees per square second? In this case, if we neglect any kind of losses, electrical losses, mechanical losses like friction and so on, okay? And finally, there is a third question here. If the rotor acceleration in the question 2 is maintained by 8 cycles, and remember we are using here 50 hertz, calculate the change in the rotor angle and the rotor speed in RPM at the end of 8 cycles, okay? And it is a very amazing and interesting question because you need to reflect about all the concepts that you saw on my previous videos, okay? Here, starting point, very simple. Let me go here. Let me open the room here for more space. And the first step is extremely simple. My students, they are extremely clever. My students, they know a lot of mathematics and they know that the kinetic energy that is stored in the rotor is basically the rate power multiplied by the rotational inertia. What I'm telling you is KE is equal to nominal apparent power multiplied by the rotational inertia. In this case, everybody knows that the rate power is 50.34 MVA, and also we know for this very specific example that the inertia constant is 6.9 megawatts per second divided by MVA. And from there, we can see that the total kinetic energy is like 350.5 megajoules, okay? That is the total kinetic energy that we have at that rotor when the rotor is spinning, is rotating at constant speed and equal to the synchronous speed, okay? What's happened if we have a power imbalance? Okay, when we have a power imbalance, that is what we call a disturbance, okay? When we have a power imbalance is because the balance between mechanical and electrical power is not longer valid. If we lose the balance between mechanical and electrical power, that means that this difference here is different to zero, and that means we have something called accelerating power. In this case, the accelerating power is 10 megawatts, okay? And that is happening inside the beautiful swing equation. In the swing equation, that is the second order derivative function here, in terms of the rotor angle, we have on this side 10 megawatts that is affecting or accelerating this machine. We assume that that happened after t equals 0. And now what we need to do is just basically extract from here the second derivative. Because all my students, they are extremely clever in terms of mathematics. They know that the acceleration, the angular acceleration alpha, is equal to the derivative, the second order derivative of the rotor angle. And from there it's extremely simple. Taking the swing equation and extract this term, that is the second derivative of the rotational speed, and the problem should be done, okay? Here we have the acceleration alpha, we have 180 constant, f 50 hertz, delta P 10 megawatts, that is the accelerating power. We know the value of the rate apparent power, 50.34, and we know H, 6.96. That means that is just question of put the number together. In this case, you can see that when we put the number together here in this equation, alpha, the angular acceleration is equal to 256.76. That is extremely simple. And the unit for this angular acceleration is electrical degrees per square second, okay? However, to be honest, this unit for acceleration is not quite useful. It's not quite frequently used. And the reason is that the acceleration must be modified and expressed in RPM per seconds, for instance. RPM per seconds is a very basic and very simple way that we can express the acceleration in something that can be used, can be feel, can be tangible for people, okay? And to convert those 256 electrical degree per square second, what we need to do is multiply and divide, and we obtain here 42.79 RPM per second. What this acceleration is telling you is if we apply 10 megawatts and we keep this imbalance, of course, in this case, the for 1 second, the rotational speed will change 42.7943 RPM, okay? What this number is telling you is, depending of the duration of this disturbance, the rotational speed will change in, for instance, in 1 second, 42.79 RPM. Now, the next question is, okay, this acceleration is maintained or is supported by 8 cycles, okay? And you must remember that those 8 cycles, we are working at frequency equal 50 hertz, okay? If we are using a frequency of 50 hertz, it's very simple to calculate the accelerating time. 8 cycles divided by 50 hertz, or 50 cycles per second, we obtain that the acceleration time in this case is 160 milliseconds or 0.16, okay? 160 milliseconds or 0.16 seconds, okay? Now what we want to know is what will be the angle that will change, how much the angle will change if we apply this disturbance, this accelerating power by 0.16 seconds, okay? And now what we need to do is, again, coming back here to basic definition, it's extremely simple. You know that the acceleration is the second derivative. From there, we can multiply by the second differential of time in both sides. And then we can apply integration, okay? What I'm telling you is that this equation can be integrated twice, and we can obtain alpha, delta as the change in angle, basically using the acceleration. And we are assuming that this acceleration, alpha, is constant, okay? I will put here again as remark, remember that alpha is constant, okay? As alpha is constant, the integration was extremely simple. 1/2 acceleration is constant, and here we have square t, okay? Now what we need to do is evaluate this equation or substitute inside this equation the time, the accelerating time. The accelerating time is 0.16 seconds, and from there what you can see over here is the result, and the result is clear and evident. During a time period of 0.16 seconds or 160 milliseconds, the angle will change by 3.286 electrical degrees. What I'm telling you is that if we have the phasor diagram of this machine, if we apply this disturbance by 160 milliseconds, that will increase, or that will modify the angle delta, the rotor angle, by 3.28 electrical degrees. And what is the final part? The final part is, let's calculate the synchronous speed. In this case, the synchronous speed is extremely simple. 2 pi multiplied by the frequency, and as you can see over here, we obtain the synchronous rotational speed or electrical speed is 314.15 radians per second. The final step is calculating the mechanical rotational speed, and the mechanical rotational speed is extremely simple. I am using the same equation that I have been using because I want the result in RPM, okay? If you look over here, we put the constant 60, frequency is 50 hertz, 4-pole machine divided by 2 in the denominator, and this is the rotational speed of this generator. In this case, the initial rotational speed is 1500 RPM. But during the acceleration time, you must remember this is the starting speed. This is the starting mechanical speed, 1500 RPM. But if we keep constant the acceleration, remember that the acceleration is constant. If we keep constant the acceleration during a period of 160 milliseconds, and that is what I am doing here, I keep constant my acceleration of 42.79 RPM per second, and I keep constant by 160 milliseconds. If we keep constant this, well, we obtain the new rotational speed. And if you look over there, in this case, the rotational speed is 1506 RPM, approximately, okay? I am telling you that is 1506 RPM. That is larger, that is above 1500 RPM. What I'm trying to tell you is that the mechanical rotational speed, the final mechanical rotational speed, is larger compared with the initial rotational speed. And that was because the delta P was accelerating those 10 megawatts that we applied that 10 megawatts at the mechanical power. We applied that delta P at the mechanical power, and of course that affect the electrical power on the other side, but also the rotational speed, okay? I highly suggest that you take again this problem, solve again this problem, but think in another way, okay? I highly suggest that instead of increasing the mechanical power, think about what will happen if you reduce the mechanical power or you increase the electrical power, okay? Think about those games, because it's very important that you think about and reflect and think about possible scenarios, okay? For power system dynamic, it's impossible that you solve all the problems. There is not a single book with all the problems because there are too many. And also, if you can solve many of them, that will not help you. What you need to understand is to analyze power system dynamics, to understand power system stability. You need to reflect. You need to think. And it's not only mathematics, it's also the physics behind the phenomenon. You can be a very good mathematician, but if you don't understand what is happening from the physical point of view, you will not be able to solve and understand the problems that you are solving. And as a consequence, you cannot get solution later when you are in your job, okay? Well, this is all for this video. It's been a pleasure having you, all of you, here in this video. If you like the video, please like or also subscribe to the YouTube channel. Thank you very much for watching. I will see you at the next video. Thank you and bye now.